This is a carbocation here, and neither one of these guys, this is deficient of electrons, right? So you are deficient of electrons. Neither one of these carbons can give you electrons, but next to you, you have these lone pairs right here. Would you be able to do a resonance form? Well, yeah, it isn't, a typical bonding pattern for oxygen, right? So this is not a typical bonding pattern for oxygen, but you will then fill the octet. Is everybody seeing? So if you are here, and now you do this, by doing this like that, even though this is weird, like so, this is now your plus, but now you have a full octet for everyone. That should be the most stable. Is everybody seeing that? Not a typical bonding pattern. Okay, this will not be your typical bonding pattern, but this is why it's there. This is one of the reasons that I like to use mastering chemistry, because oftentimes, I don't do something that other books have. Remember, the voice that you get is my voice using Wade. And there are like 7 different textbooks that are used nationwide. And so these people nationwide are the ones that are coming together to create all of these questions. And I selected this question because I knew I have not gone over this, okay? So hopefully that people would have spent time with it. Okay, so what about this one? I hope nobody saw it. What about this one? Would it be the one at the top or the one at the bottom? Think resonance. Think resonance. Would you be able to move this pi bond here? Can I do this? Yes or no? Well, I can do whatever I want. But will that carbon accommodate it? Yes or no? No, because that carbon looks like this, right? Like here you have this, and that carbon looks like so. That carbon is saturated. That carbon really cannot accept a pi bond. Is everybody there? So even if you wanted to do this, excuse me, that doesn't work. Everybody, that just does not work. What about at the structure below? The structure below, if you were to do that, that simply can occur because this guy has the double bond there, right? And then here, you're empty, right? Can you see that? So I can move that here and end up with another structure, and you can move it back. That will be the more stable. So the more resonance forms that you can generate from one original ion, the more stable that ion is. Okay, if you can share the wealth, like they say. So if you can share your negativity or your positivity through more than 2 atoms, that structure is said to be more stable. Okay? And then if you come over here, and I think there were 2 more, hopefully you'll be able to answer that question now. Top or bottom, which one is the most stable? Stable. Top or bottom? Does everybody agree in bottom? Everyone agree in bottom? You're right, is bottom. You can move that pair of electrons out. Okay, then you will end up with this resonance form. And this resonance form now will be the double bond is here, and your plus is in that spot. Okay? And the very last one, which is more stable, top or bottom? Top or bottom? Can you do anything with this charge here? Nothing. I'm saturated, you are saturated. You cannot bring, there's no pair of electrons to do anything, right? So you're done. But here, this nitrogen has a pair of electrons. If that nitrogen were to create a double bond here, now you have a full octet. Now the charge is in the nitrogen. Now the structure is more stable. So the bottom one is more stable. That's the criteria that they wanted you to do with that. I heard people saying, I never got to see the right answers. If it is a multiple choice like this, you're not going to get multiple tries. Sorry, the next example, the next chapter 2, which is due this Sunday, chapter 2, which is due this Sunday. If there are drawings, you're gonna get the opportunity of seeing more than one time to try, okay? And the answers are open after everybody finished, because we are a community of people telling everybody what to do, and it's quite unfair that one person that tried the times and get it wrong tells the other one and gets it right. So the answers do not open until the assignment is completed, which means the Sunday at midnight, okay? So that's how that story goes. Okay, so is that, everybody okay with that? This is the questions, right? Laura, that was it? Okay. All right, I want to continue with chapter 3, and I feel so badly because this time of chapter 3, I went to, I just want to, oh, I'm sorry, here we go. Here's a PowerPoint. There are some examples that I wanted to show. And in these examples that I wanted to show, we have the numbering of the main chain. You know, so they're saying that when you're numbering a chain, you know, like you looked at this and it looked obvious, and this to me is like incredible. They're saying that that would be incorrect, and that the correct way would be, why is that incorrect? Isn't this the exact same thing? Oh, I'm like, what? All right, I think I do much better with the example, so I don't think I can even explain this one. So in this example, they're starting numbering from the very top. So they give you now already the substituents on carbon 3. And the story is that if you can start and have the substituent at the lowest number possible, that's what you really, really want to do. So only when numbers are not equal, when numbers are equal, is that you're looking at then having the alphabet column. I like this slide. All I did here was come up and just review. So all we're doing is kind of like review so far. That, you know, if you just, the alkyl groups, we did that one when you removed them from the first carbon. And then we had these here that we said you have to memorize. I know that some of you were like, so you have to memorize the isopropyl even though we know the new nomenclature, right? Everybody knows. So you have to have the propyl memorized, you have to have the isopropyl memorized, even though now we know that that isopropyl is called parentheses 1-methylethyl, right? And that this isobutyl would be parentheses 2-methylpropyl. And that the sec-butyl parentheses is 1-methylpropyl. And that the terbutyl parentheses was 1,1-dimethyl ethyl. And it's very logical in my mind. For all the corrections that IUPAC has done, this by far makes the most sense, because that being this one here called a sec-butyl, right? This one here called a sec-butyl is great, but when you attach it to a carbon chain, it became a tertiary carbon, right? So it didn't make any sense. The only reason why I'm starting with this is I don't think I said this in your class, so I want to make sure that I brought what I didn't say in your class here. If you were to use this historical nomenclature, it will be the I that gets organized alphabetically. It will be the I. Take a look that there is no hyphen breaking it. Is everybody seeing the difference? Here's the difference. When there is a hyphen breaking the name, then the B is what counts for the alphabet. So it will not be the S, and it will not be the T, it will be the B. All right, it will be the B. And again, your book goes ahead and explains something, I don't know. I don't want to, these are silly things. And this is even silly things too. But, so give the structure of 4-isopropyl octane and 5-terbutyl decane. Would you be able to draw? The answer is of course. So go quick. Go quick. Would you be able to draw? Go quick. I told told you it's not my typical lecture today, all because I'm getting to physical properties and I need the slides. So sorry. And I assume that if you draw it, it's gonna look like that, right? If we're drawing it, we're gonna call it like that, right? Everybody kind of drew it like that. I did not draw mine like that. I don't know what you've drawn, but you know, I'm not drawing anything like so. So can I show you how I'm gonna draw this? This takes too much time. I hope everybody realizes this takes way too much time. If you're taking a test, this is way too much time. I don't know why they're doing it like that. The whole world is going with the line angle drawing, okay? So I will quickly do mine like so. So 1, 2, 3, 4, 5, 6, 7, 8. Did you do it like that, or you were doing the cha-chas over there? You were doing the CH3s? Okay, so don't do CH, well, you do whatever you want, but I can tell you that that takes time. All right, that takes time. And then when you go to do the 4-isopropyl, it doesn't matter if you start 1, 2, 3, 4, or you start 1, 2, 3, 4. So it doesn't matter, you know, when I'm grading the test, I see people that have the isopropyl this way or the isopropyl the other way. And I think you all know that this is no longer gonna be called isopropyl, that this is then gonna be called your 4, and in parentheses, your 1-methylethyl. Ethyl octane. Okay, the same thing when they want to do 10. When you're doing 10, you're doing all of them like so. You're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And on carbon 5, 1, 2, 3, 1, 2, 3, 4, 5. So if I'm coming here, I put the little T to the bottom. So there's my T to the bottom. So all I'm trying to show is that you do not have to draw it like they do. Okay, you do not have to draw it like they do. And so that would be that name here. Okay, I want to add one more substituent to this. Okay, let me see if this came out right. 1, 2, 3, 4, 6, 7, 8. Okay, put 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh shoot! That doesn't exist. So it looks like that. Okay, so it's like so. Would you be able to name it? The answer would be yes. Okay, the answer would be yes. And the only reason why I'm putting this one here is because, of course, you would think that you would start this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But in reality, if you started from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then you would take this complex, right? Because this, if you had to name it as a substituted substituent, this would have been what? As a substituted substituent, what would this guy be called? 1, 2, 3. So this would have been called 1, 2 dimethylpropyl, right? But if I start from here, then all you would have is a propyl. Is everybody following? I mean, this is like a bad, I think having that glob there, that did not help me at all. So this, you would start numbering this chain here as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then how would you name this guy? Yes. That's right. You want the most little groups around the sides, yeah. And I'm gonna draw another one and I'm not gonna mess up. Okay, I'm drawing another one without messing up. So we know how to name this one already, right? Sorry, I'll do a better one without messing up, I promise.
For that one, we name the methyl first, and then move on to
Okay, one moment. All right, what did you say, I'm sorry? All right, so this one now, let's go back and answer this question, right? So we have then substituents are, on 2 and on 3, I have the dimethyls. On 4, I have a propyl. And then on 6, I have a 1, 1 dimethyl ethyl. Yeah? So those are the substituents, and now we're gonna write the name out. So writing the name out, we have to pay attention on the alphabet. So the alphabet, this will be the first letter that will get alphabetized. The P for the propyl and the M for the methyl. So if we're writing the name, this will begin with a 6, 1, 1, dimethyl ethyl. This 6, 1, 1 dimethyl ethyl. Then I'm gonna go to the 2, 3 dimethyl. Bless you. Then I'm gonna go to the propyl. And at the end of all of this is decane.
You said in the previous class that was naming the ones in the parentheses with the priority, right? Or
Right. Right, so when you're naming, when you're organizing in alphabetical order, okay, so when you're organizing in alphabetical order, if you are in parentheses, the first letter of the word in the parentheses is the alphabet that you're going to use. So even though it's starting that you have 2 of the methyls, it doesn't matter, those are the rules for that whole concept. Okay, one of the things that I have to do is actually talk about physical properties. And physical properties are, what are physical properties? Help me out, I'm gonna switch it to the PowerPoint. What are physical properties for our compounds? What were physical properties? Okay, there are things, she said there are processes that will not change your chemical composition. So keeping in that thinking process, physical properties are the color of the well, it starts out as physical state. So if you have a liquid, gas, or solid, that's a physical property already. You would describe something. So the liquid is stinky, the solid is yellow, the gas I can't see, right? So you describe something. So, and then after that, our process that you don't change. So a boiling point is a physical property, a melting point is a physical property, a density is a physical property, solubility is a physical property. Do you solve or do you not, right? So in that trend, just like you had periodic trends in Chem 1 and 2, and your periodic trends were just basically on the periodic table, we also have these trends, and they would always be the same. So the first one that happens is this boiling point for these alkanes. Remember, we're in the chapter of alkanes. And what we find, and it makes absolutely a lot of sense, is that as the compound gets larger, the boiling point is increasing. That makes sense, right? So with an increase in size and in mass, there is an increase in boiling point temperature. Is everybody okay? That makes sense, that's a trend. And then we have these isoalkanes, and isoalkanes are obviously a branching. So we have what are called straight chains, and we have the branched alkanes. We see that the branched alkanes have, again, the trend seems to show that as the mass and the size get bigger, the boiling point also goes up. But we do see that their boiling point is a little bit lower than the straight chain alkane, okay? So this is what I know, right? This is what you really, oh, I don't wanna see that. All right, you don't wanna, this is why I hate PowerPoints, really. This is why I hate PowerPoints. All right, so this is the boiling points. All right, so does that make sense? Yeah? Okay, let's take a look at the melting points. The melting point of these alkanes is crazy. Take a look at the trend. The trend says that the even numbers will have a higher melting point than the odd numbers. Do you think I'm gonna remember that? I don't think so. Okay, yeah, melting point increases as the carbon chain increases, I know that. But it's saying that alkanes with an even number of carbons have a higher melting point than those with an odd number of carbons. I don't know. I probably will never ask that in my life, but here it is, okay? And then I'm gonna switch you out of this, because I don't want you to see all these other ones that I'm gonna see, that I hate these things. All right, and we start drawing again. So we got to methane and you started to draw, okay? We started drawing in methane, you did all this, right? So you've done all that in that lab. And then you did all this, okay, you did all that. And then we got to ethane. And in ethane, we saw something that looked like that, but you may not have drawn this the way that I see it, okay? And what they're saying is that you have two conformations, and the conformations look like this. I don't know if I'm able to draw this correctly. I didn't bring my CD or the computer. All right, so let me attempt to draw, okay? Let me attempt to draw. And let's see what we mean by this. And then we're gonna make life simple because somebody came in to simplify my life, okay? If you draw in the wedges and dashes, and these are conformations, conformations are you are going to rotate a carbon-carbon single bond and you're gonna see something different. Okay, so conformations are different arrangements of atoms caused by rotation about a single bond. All right, so we start out like this. Usually this is how we're gonna draw in a perspective drawing, and I'm assuming that you all drew in a perspective drawing, but the drawing of an ethane in a perspective drawing looks like these. Anytime you have a solid line represents you are on a plane. So it's like you have 109.5 to that hydrogen, 109.5 to that carbon, 109.5 hydrogen and carbon, and then you have one hydrogen that is coming to the front, and another little hydrogen that is going to the back on that carbon, and the carbon neighbor will have the exact same thing, one hydrogen that is going to the back, and another hydrogen that is coming to the front. If I decide to rotate this bond, if we say go ahead and rotate, so we say rotate, And rotate means that I hold on to one and spin the other. Is everybody there? I'm holding on to one carbon and I'm spinning the other. Is everybody okay? I rotate. So this carbon I'm gonna leave the exact same way. And that carbon that I'm leaving the exact same way has all of that. And I rotated the other. And when I rotate this one, it's gonna end up looking like that.
You can't see it.
End up looking like that. And that is a rotation. Somebody by the name of Newman decided that he could not do this. The gentleman is named Newman. And these ones are gonna be called the Newman projections. Newman says, I'm not gonna do this. So Newman decided that he's gonna be using this concept of a Mercedes-Benz. I don't know if you know the symbol of Mercedes-Benz is that Y, upside down Y. And that upside down Y, this is going to represent, that represents your front carbon. Kind of ridiculous because here you only have one front carbon and one back carbon. Can everybody see? One is front and one is back. The back is represented with a circle. So your back is represented with a circle. So that circle represents the back carbon. What you're not seeing here are the hydrogens that are on this, okay? What you're not seeing is the hydrogens that are on this. All right, so for this structure, I'm going to start with this drawing. And this drawing is going to show up like this. This is my front carbon, and this is my back carbon, okay? On my front carbon, which is the Y, I have hydrogens on it. And on the back carbon, I also have hydrogens on it. Okay. When the hydrogens are like this, you have the carbons and your hydrogens are behind it, and you don't see anything, those hydrogens that are right behind you, this conformation is going to be called the eclipsed conformation. This is called eclipse. The word is eclipse. The majority of the books rotate the front carbon. Your book rotates the front carbon. I have such a hard time going from a bottom Y to a top Y to a bottom Y to a top Y. I, for years and years, just rotate the back carbon, and then it all stays the same way, right? So if everything stays the same way, my front still holds all to the hydrogen. When I rotate the back, the rotation of the back has the hydrogens going that way. And when you get to see all the hydrogens of ethane, this is going to be called staggered. And every time you do the rotation, you have gone 60 degrees. And if we do another 60-degree rotation, where are we going to be? Okay.
At eclipse.
Let's take a look. Let's take a look at the PowerPoint and see how your book represents this and see if this is helping. So first of all, we already explained what conformations were. If you take a look, because this is a single bond, because that is a single bonds can rotate. So you can actually keep one the same and you can rotate the other, is what they're saying. So you can keep rotating the other. That rotation will lead to a different conformation. But in the case of ethane, it seems like everything is exactly the same way. So when I come over here and I see that I drew that like that, and I drew mine just the opposite way, can everybody see that I drew mine the opposite way? I had the hydrogens up and down. Newman says, forget it. Forget about trying to draw this like so. Let's go ahead and come into this Newman projection. The inverted Y representing the front carbon, and the circle representing the back carbon, okay? They like to rotate the front, but again, I've been teaching this for 21 years, and I have tried rotating the front, and I have tried rotating the back, and I have had more success with students rotating the back than rotating the front. I leave it up to you, right? I'm gonna leave it up to you, but I think it will work better if we all speak the same language. So let's go ahead and just rotate the back, understanding what your book is doing. Is everybody? So here comes the book, and somebody takes the time to do this. Okay, so somebody goes in and takes the time to do this. You will always, these are confirmations of everything, but look how they start. So forget about everything else. We start over here. Okay, and we start over here always with the eclipse drawing. Okay, so you always want to start with the eclipse drawing. The eclipse drawing is where you have all of the attachments to the carbon behind one another, okay? So all of the hydrogens are eclipsing one another. And then if we spin the back, see what I'm saying? They're spinning the front. If I spin the back, I don't have to keep changing the Y and the whatever you call this. What do you call this? Mercedes. You don't have to go from Mercedes to Y to Mercedes to Y. All you're doing is moving the hydrogens around the Mercedes. How's that? Is everybody there? But all we see is that it doesn't matter every single time you're eclipsing the same atoms and you're staggering the same atoms. But somebody took the time to measure the energy behind keeping hydrogens behind one another. Okay? That energy is called a torsional energy. Torsional energy is there is energy that I have to supply to keep you behind me. I don't want you in my space. You know how you talk to some people, especially tall people, for me that I'm short, and they come and talk to you and they're like here and you feel like their face is like their body is on your body. I think people have talked about that, your personal space. That's the same thing. It's like these torsional, you're like in my space, get away from me. When you get away from me, there's a relief in that torsional space, torsional strain. It's called a torsional energy, and I'm not going to remember 12.6, but I certainly will remember the 3.0. Is everybody okay? More or less. Let's go to propane for a minute. Okay, let's go to propane. And how do we turn this information that seems so simple, but like what's the point? Right? Is everybody there? I mean, I'm like, what's the point? Let's get to propane and see what we're seeing. All right? So when I get to propane, I'm going to say something like this. Draw the eclipse and stagger conformations of propane. Okay? And so my recommendation to you is that we always have something that we grab on to figure it out. So I will start by drawing propane now like this, because I don't know really what she talks about. Because remember, in Newman, there's only a front and a back carbon, and they are adjacent to one another. Okay? So it's either this is going to be the front, and that's going to be the back. Is everybody there? So I'm going to keep the front in black, and the front has 1, 2, 3 hydrogens. And I decided, because I wanted, that this is going to be my front carbon. Somebody in the back could have selected to be that one, and they would have been exactly the same. And this is the front carbon. okay? The back carbon now is this beautiful orange color one. And this beautiful orange color one that I'm gonna call now my back carbon. What do you have on it? You have 2 hydrogens, she says. So you have 2 hydrogens, and you have a methyl. Okay, so you want to collect like terms. You don't want to be attaching the carbon to the hydrogen to the hydrogen. So that's going to be mine. That's going to be my back carbon. So I'm going to come over here and I'm going to draw Newman, because they say if they want you to draw eclipse and staggered, it's Newman. So they're not going to say it. You know that this is referring to Newman projections, right? That's referring to Newman. So I'm going to come over here. I'm going to use a different color. And I'm going to do my circle. And in the front, I had a hydrogen, and a hydrogen. And to make life a little bit more spicy, the back one, I'm going to put the methyl, the hydrogen, and the hydrogen. Like that. And everybody knows that this one is called eclipse. Okay? I'm holding the front and I'm spinning the back. I'm holding the front and I'm spinning the back. Right? If I'm spinning the back, my hydrogens stay the way they were. Spinning the back, methyl is here, hydrogen is here, methyl is here, and this is going to be called now staggered. If we do this all around the ring, eventually, if you go 360 degrees, you will end up back over here. Is everybody following what I'm saying? This is going to be number 1. This is going to be structure number 1. This is going to be structure number 2. Everybody understanding? I'm going to keep spinning. So I did a 60 degree. This was 60 degree. And then if I do another 60 degree, I would have gone 120 degrees. And eventually, I would do the whole rotation to end up over here. Yes? So what would be the eclipse numbers if I follow that? What numbers would be eclipsed in this? So it'd be eclipsed would be structures 1, 3, 5, return back to 7, which is 1. Is everybody? And staggered would be the 2, the 4, and the 6. Is everybody okay? I mean, I'm missing my power, my little ChemTV. I'm missing my ChemTV. My question to you, are all the eclipse conformations at the same energy level? Are all the eclipsed conformations at the same energy level? Yes. Why is that? You're always going to be eclipsing a hydrogen and a methyl, a hydrogen and a hydrogen and a hydrogen and a hydrogen. It doesn't matter where you go. Okay, be with me. Structure 1 eclipse, hydrogen and methyl is here. Conformation 3 eclipse, it will be hydrogen and methyl here. Number 5, it will be hydrogen and methyl here. And number 7, I return to the same. So all conformers, eclipse of propane are the same. Will the energy be higher or lower than in the case of ethane? The torsional energy. Torsional energy, you're behind me. Will that energy be higher or lower than in the case of ethane? Should be higher, right? Because in the case of hydrogen, the hydrogen is a small atom and you have it behind you. In the case of hydrogen and methyl, now you have hydrogen and a carbon, and this carbon now has hydrogens that are doing this. So the expectation is that the torsional energy in propane will be higher than the torsional energy in ethane. When we go back, and we look at the famous PowerPoint, we see that this torsional energy for ethane is 3. So I'm going to memorize that so much easier. I'm going to say every time I'm eclipsing hydrogen, it's about 1 kilocal per mole behind one another. I have 3, so 1, 1, 1, 1, 1, 1. I'm going to make it simple. I don't think it's like that, and I don't care. I'm just going to memorize it one way. Is everybody there? When I get to propane, take a look at propane, and again the same thing. You take a look at propane, the same thing. Your perspective drawing, now you know how to draw. We're going to Newman, exactly like I said. This one will be representing your staggered, right? Everybody can see that this is staggered. Staggered is when you see all of them, okay? Staggered is when you see all of the atoms that were attached to the front and the back carbon. When I do the energy diagram, this is called an energy diagram, and it's called the dihedral angle. Take a look at what happens. 3.3. Is everybody seeing that's 3.3? So having a hydrogen eclipsing a methyl really increases the torsional energy by 0.3 kilocal per mole. So the bigger the groups, of course, the higher the torsional energy to keep you into that eclipse conformation. Is everybody okay? I know, you're going like, what is the point of this? Right? What is the point of this? Don't ask me, I just teach the class. We see it, no we don't, we just establish things. So if I go to butane, can you imagine how boring this is gonna get, like this? If I were to go to butane and I am not specific, and I say go to butane and you add another carbon here, and you're looking through the front and the back, what will be the difference in your structures? Exactly. Is everybody seeing? The only difference is that CH3 is going to be an ethyl. The eclipse and staggered are exactly the same, no? And the expectation is, of course, the energy will be higher, because now instead of having just one carbon, you have one carbon that is doing all of that, and there's another carbon over there that is doing all of that. So the torsional energy should increase. So very boring was that. Yeah, they spin. In real life, they spin, yeah.
So for butane, the energy level would be approximately 3.6, and it would increase by 0.3 for each.
I don't know that. And they don't have it even in the books. So that story ends right here. They want to see another story, yeah. So they want to see a better story, because these stories get ridiculous. And organic chemists, well, at our level, nobody worries about what is the difference. I mean, the assumption is that it's going to get higher, and it does get higher, but you don't even have to memorize it. So let's get butane and get it a little bit better than that, okay? So if we decide to get butane now, so I go draw conformations of butane. Between carbons 2 to carbon 3. This is what we call that. So draw conformations of butane between carbons 2 and carbon 3. So, back again. Remember that a lot of what I try to do in teaching is creating a process, okay? We're creating a process of thinking on how to do this. First thing I do is I structurally draw my butane. And I know that this is going to be then carbon 2, and this is going to be carbon 3. And it doesn't matter if you start from the left or if you start from the right. My carbon 2 is going to be black. So in my carbon 2 that is black, what do you have on carbon 2? You have a hydrogen, and you have a methyl. That's what you have on carbon 2. Yes? And on carbon 3, that is gonna be pink, I have a hydrogen, and I have a methyl. Okay, and you wanna start with what can possibly be the highest torsional energy of the conformer of butane. The highest, okay? So if we start out with the highest, the mentality is, at the highest, I'm gonna have a methyl in the front, a hydrogen at the bottom, and a hydrogen at the bottom. Highest, what am I gonna do with the back carbon? Highest in energy, what shall I put here at the top?
A methyl.
Can everybody see you should put a methyl right here? A methyl should be there. And that should be the highest. I don't know. Let's see, she wanted me to start out like that. I do 60 degrees and I have a staggered. Let's see how that staggered looks like. When I do 60 degrees, rotation, and I have a staggered. And I rotate. Like that. And if I do another 60 degrees, if I do another 60 degrees, what do I have? If I do another 60 degrees, what do I have? That methyl now comes here, right? If I do another 60 degrees, that methyl comes here. There's a hydrogen here, and there's a hydrogen here. Okay, so this is a good moment to pause and look at the two eclipses. Okay? So we're looking at that eclipse and we're looking at this eclipse. Would you think that these two eclipses are the same in energy? I think everybody can quickly say no, right? I think everybody can very quickly see that they are not the same. It takes a lot more energy to have two carbons with all of their three hydrogens in my space and doing this. Because you're behind me, that's torsional, and then steric is you're like this, in my space. You're in my space and in my face, okay? So in my face is that torsional, and then not only are you in my face, which is torsional, but then if I look down, you're doing this, which is now in my space. So in my face and in my space is what's happening here, all right? So yes, we see that they are two eclipses, but that the energy is different. If you see that this should be higher in energy, this one is going to be then called totally eclipse. Sounds like a song. A total eclipse of the heart. That's why he took organic chemistry, whoever his name was, okay? He took organic chemistry and go, oh, that's totally eclipse. All right, so that's totally eclipse, and this is eclipse. There's a song like that, isn't it? Mm-hmm. Total eclipse of my heart or somebody. All right. So this is what they're saying, right? So your book in this flat way of looking at things. I promise Monday we'll look at my Cube Chem TV. So your book in this flat way of looking at things. So take a look at these butane conformations. So if we take a look at them, I will drop the glass now. But anyway, we are doing the rotations, right? We're doing the rotations like so. That's what I was trying to get when I say look at butane three different ways. Remember what I kept saying, look at butane? Actually, this is what I was hoping you would be seeing. But we were looking at the molecule like that. We were not looking at the molecule through carbons, right? So we can see that we're always going to start with the two largest group eclipsing one another. That is the criteria. You would like to begin with the two largest group eclipsing one another, if there is a difference, right? So far, there hasn't been a difference from ethane to propane, but in butane there is. So those two big groups eclipsing one another, that's gonna be the label totally eclipsed. And you wanna start with the highest, I'll show that momentarily. And then you do your rotations, and like I said, these guys rotate the front and the back, and I find that very distracting. But we see that when we get to the other eclipse that we drew, right, when we get to the other eclipse that we drew, the energy is less. So let's take a look at the staggers that we've drawn. When I take a look at the staggers, we did that. Let's rotate again, okay? Remember, your rotations always go from eclipse to stagger to eclipse to stagger. So for me to get to the other stagger, I have to get here and I'll rotate again. And when I rotate again, right, I still have the methyls, the hydrogens, and the hydrogens. When I do my spin, now I have the methyl is gonna be here. The hydrogens are gonna be like that. And yes, these guys are called staggered and staggered. They're both called staggered and staggered. But are they the same in energy or not?
No.
Do they seem to be the same in energy or not? The answer is not, okay? They are not the same. When your groups, take a look that, in a way, to use this terminology that we're gonna start using right now, you really have 4 hydrogens and 2 other things. So there's a total of 4 hydrogens, 1, 2, 3, and 4, and your 2 groups are 60-degree dihedral angle from one another. Okay, or over here you have 1, 2, 3, 4, and your 2 groups are at 180-degree dihedral angle from one another. When you are 60 degrees from one another, you are called gauche. French, does anybody speak French? People were speaking gauche. Oh, we're not seeing these colors so hot. Okay, so 60 degrees to the right, which would be clockwise for us, or to the left, which is counterclockwise for us, is called the gauche. Or if you're at 180, this is called the anti. They are also called staggered as well. So if I had to, create your energy diagram, right? We're creating our own energy diagram. What follows here? Remember how we used the 1, 2, 3, 4. What's missing is what? 5, 6, and 7. Okay, is everybody okay or no? Okay, what are 1 and 7 are what? Totally eclipsed are 1 and 7. I'm helping you for the discussion packet. What follows? Eclipse are what? 3 and 5 is correct. 3 and 5 is correct. Staggered, are they all the same? Are any staggers equal in energy?
2 and 4.
2 and 4 are equal in energy. And then the lowest in energy,
No, 2 and 6 are equal, and
2
then
and
4 is
6.
the anti.
okay, many of you are going, what? Okay, and 2 and 6 are equal, sorry, and then 4 is to itself, and energy is increasing in that direction. So if anybody said to go ahead and draw, right, if anybody said to go ahead and draw, and I don't even have a, anti-staggered is the most stable. Somebody said to go ahead and draw, I would go ahead and start here. So this is 1, and 2, and 3, and 4, and 5, 6, and 7. And 4 is at the very bottom. Okay. then it follows to be 2 and 6, which are the same energy level. Higher yet are your 3 and your 5. And at the very top are your 1 and your 7. And you were then to connect the dots. I failed connecting the dots. There are many skills that I actually have not accomplished well. You're seeing them all. So I don't leave many out. I disclose all. So this will be my energy diagram for the conformations of butane, looking at carbons 2 and 4. And 3. 2 and 3. Yes.
You said when we first start out, we're supposed to start with the highest something
Torsional energy.
torsional energy.
Right, the highest torsional energy, and that criteria is going to be the 2 largest groups behind one another. Yeah. Your book again does everything differently than the whole world. I'm sure, well, that me does. I think, and that's the whole world, isn't it? All right, so this is how the book chooses to do. The book decides, okay, I get all of that, and then I'm gonna go ahead and draw. Oh no, why did I let it happen? So the book did draw it like I did. So, so you would start with a potential energy at one spot, and then you would look at the conformations around it. Okay, take a look that just like you did. Can you imagine me asking you to do this on a test? Would you imagine me asking you to do this on a test? The answer is no. That test will be like a lower level class. That's not what we teach. We're teaching a higher level class here. This is busy work, okay? This is totally busy work. But I think if you were asked to look at a molecule, right, any other molecule, I think that you should be able to come up with a decision that yes, it makes sense that it will be much greater in energy, and this is called a torsional energy. Eclipse, relieving the molecule, keeping a molecule behind one another, all those atoms behind one another, takes energy. Your molecule is more stable when everybody is away from your space, okay? That's what they call the 0. You're at the lowest energy level when all of these atoms are as far apart from you as possible, all right? If you start putting atoms behind me and in my space and spinning, my molecule is unstable, and it takes energy to keep it that way, all right? So that is the mentality. Anytime you have all these groups behind me, it takes energy. How much? 5 kilocalories. So having methyls behind me, look how much greater. Take a look at the energy as you go to staggered, right? So we're looking at these numbers. We really are looking at, I don't ask for numbers, okay? So I never ask people to memorize numbers or none of that. We're just using this so we can just really think. But we start here at 0. So this is the start at 0. And then immediately 0 is when you have them as far apart as possible in the staggered, which is the anti. And then when you are gauche, even though you're far apart, there's a little bit of a steric here, right? This is called a steric, kind of like you're spinning right there. And that brings the energy a little higher. Gosh, this is terrible coloring. Is that better? Is that better with that light off? And you can see that here the same and the same. As your hydrogens and the methyl eclipse one another, the energy goes higher. Now you have, oh, you asked that. No, you asked something else. Remember when you had in the case of propane? In the case of propane, you had one hydrogen and a methyl, hydrogen and a hydrogen. Do you remember that that was 3.3? Do you remember that? When it was propane, a hydrogen eclipsing a methyl, it was 3.3. When now we have 2 hydrogens eclipsing 2 methyls, it went by another 0.3 factor to 3.6. Yeah? 3.6. And then when you have the two menthols eclipsing one another, it goes to the highest, which is now the 5 kilocalories up here. There is a big section to do in the discussion packet. I don't know, we don't have a Monday class. So this is how I'm seeing things. You have the discussion packet? I thought somebody, oh, good, it's right here. All right, so this is how much, I don't see you Monday. We already know that Monday is Memorial Day. And students are, no, Labor Day, okay. Some people said, oh, okay, Labor Day. So Labor Day means that I work more than before, because then I have to get all my housework in place. Okay, if you're looking at, she's already taken stuff out of the packet. All right, so already we've done 1 and 2. And we haven't finished all of 2, but there's very little, right? We finished all of 1, we've almost done with all of 2. I would love to say, hey, we have Monday next week, that is Labor Day. Wait, this is how the calendar goes around here, okay? So the calendar is showing, okay, momento. Where's my calendar? All right, so September the 7th, we're off. 14th, we see each other. 21st, we see each other, and the 23rd is exam. Yeah? Yes, September 23rd is the exam. So, September 23rd is your exam, so I'm recommending that you go ahead and work on discussion 2, 3, which is all naming, 3, which is all naming, discussion 4, which is all naming. When you turn discussion 4 in the back, we have already gone all the way to 5. So 3 and 4 all the way through 5 is what you're doing. Discussion 3,